Hi students, this is a screencast on the history and utility of complex numbers. This is a talk that I gave at a conference, and I had some missing steps at that point, and later on I filled them in, which is why this file is called plus. Um, and the history is very interesting, and also, yeah, enough said. Uh, so the first appearance is comes up in the formula for the volume of the frustum of a regular square pyramid. A frustum means a strange word. It means that you take a regular square pyramid, which means that the vertex, the top point, is right over the center of the square base, and you slice it parallel to the square base, and you just take the bottom part, and the bottom part is called a frustum. So in this case, the side of the base, the square base, is A. The side of the smaller square cut is B, and the height of the frustum is H. And it turns out that there's this formula. The volume is 1/3 the height times a squared plus ab plus b squared, where a and b are the edge lengths, as I said. And these are the algebraic details of that. And this is what I want you to do for homework, to go through this a little more slowly. So I'm just going to give a quick outline here of the steps. You have a proportion, and if you look at the diagram, you will see that this comes from similar triangles. And then from that proportion, you get this, which is x plus h equals ax over b. Then the volume of a pyramid is 1/3 the area of the base times the height. So the volume is going to be 1/3 a squared times the height, which is x plus h of the full pyramid, minus the volume of the smaller pyramid. And then there's some algebraic steps here that are done that are a little tricky, and they come from some of the work that's done down here. So x plus h, it turns out, is equal to ax over b. That comes from this up here. And then from that, you immediately get to this. There's some missing steps here, and the missing steps are down below. And then from here, you get to a proportion here. And so you can, and this will be used. So you substitute, I haven't looked at this in a while, but I want you to be able to follow these steps. So x plus h is equal to ax over b, so that's what's done here. Instead of x plus h, we have ax over b. And then we're just multiplying by b over b to get a common denominator of b. And then if you put that together, you get this, x over b. But then x over b from this part is equal to h over a minus b. And so that's what's substituted here. And then a cubed minus b cubed is the difference of cubes. And that factors, or you can do the division. And you find this is the only real application I've seen of being able to factor a cubic. So you actually get this formula. And we want the formula not to have an x in it. So that's why we do all this algebra, to get rid of that x and just have the formula in terms of a, b, and h. All right, so that formula comes up fine. And then, as it says here, while correct, this result does have one very slight stylistic flaw. And that is the values of a and b are directly observable, but h is not. H is kind of inside the figure. It's not something that, if you're given one of these things, you can measure. So it would be better to express the volume of the frustum in terms not of h, but of c, the slant edge length, which is an observable. And this was first done in the 1st century AD by Hieron of Alexandria. You may have heard of him from the formula for the area of a triangle in terms of its sides only. If not, I can tell you about that in class. In any case, this was done. And to use it, to develop the formula, we use the top view diagram that's to the right and find P, which is the projection of C on the base. So in this diagram, here's C, and if you project that with this perpendicular on the base, this part is where the P is, right here. So that's P. And then if you look at this diagram and follow the missing steps, we get an expression for H in terms of A, B, and C here. So I'm going to leave it to you to try to follow that algebra. Okay, and then from a talk in 1897, this is relatively new, it says that we find the square root of a negative quantity appearing for the first time in this book that Hieron of Alexandria wrote. And after having given a correct formula for the determination of the volume of a frustum of a pyramid with square base, and applied it successfully to the case where the side of the lower base is 10, upper base 2, and edge 9, the author endeavors to solve another problem where the side of the lower base is 28, the upper base is 4, and the edge length, that is to say C, is 15. And when he tries to do that, he winds up with Hieron, or his copyist, whoever, got the square root of negative 63. And he just wrote it as the square root of 63, ignored the negative sign, and continued. And the question is, why did the square root of a negative number appear in the first place? And the missing steps, if you follow this through, shows that the square root of a negative number appeared because this is an impossible situation. You can't have a frustum with those measurements. And this shows why. So that also I want you to go through a little more closely for homework. Okay? And what this indicates is a natural aversion to incomprehensible or unexpected results. If you get the square root of a negative number, the first thing you want to do is just get rid of the negative sign. And people want to do this, and mathematicians did this. Kind of interesting. All right, much later, in the 15th century, Pharaoh, a mathematician, and math was very big at this point in Italy, the Renaissance, in the University of Bologna. And at that point, as it says, there contests were held and prizes were given for a solution of various kinds of cubics. And it's interesting to note here that even at that time when they were doing this very complicated algebra, x cubed plus px plus q and x cubed equals px plus q were separate equations because mathematicians were still uncomfortable with negative numbers at this time. And in the contests, p and q were always positive. Now, of course, we realize that this is an example of the use of negative numbers, that once you have, if you've solved x cubed plus bx plus q, you've solved this one also, because you just make it negative. You pull it over to the other side. So this was the way he solved this equation, x cubed plus px plus q and equals q. Incidentally, any cubic, even with a quadratic term, can be put in this form. It's possible to make a linear substitution that eliminates the quadratic term. I'll maybe do that at a later time, but it's kind of interesting. So here's the cubic, and he made a brilliant leap. How do you solve this thing? He let x equal u plus v, realizing that the solution of a depressed cubic should be the sum of two terms. All right? And so he let x equal u plus v and substituted u plus v in there and got this. And then here are some algebraic steps that I want you again to go through a little more slowly. And so if you go through these steps, you wind up with something like this. Well, not something like, you wind up with this. And now he made two equations. He let 3uv plus p equals 0. And if that's the case, then u cubed plus v cubed equals q. All right? And then because 3uv plus p equals 0. So that's the other equation that follows. And then solving these two equations will give a solution to this, this complicated u cubed plus v cubed equation. So here are some algebraic details that, again, I want you to look at more slowly. And in the talk, I didn't do these missing steps, and I filled those in later, so you can look at those. All right. There's a nice comment here that's important, and that is, in hindsight, we see why x equals u plus v and u cubed plus v cubed equals q were important equations, and that is the problem was too hard. The problem was too hard without having some idea of the answer. And then, as long as p and q are positive, you can always solve for x. Every cubic equation has at least one real root. So that's not surprising. If you think about the graph, it always is going to cross the x-axis at one point. So why did I bring this up? And I brought it up because a very interesting thing happens here. Okay? So you can read this. I don't need to go over that part. Here is the crucial thing, and that is Bombelli, who was a follower of Cardan, and this was actually earlier. Well, no, it's at the same time, in the 16th century, saw that there was a dragon lurking in this formula. So this is the cubic formula, the solution to x cubed equals px plus q. So we went around it the other way. Yeah, so the original one we solved was x cubed plus px equals q, with the px on the left side. And then that's what this part shows that you can easily, using negative numbers that we know, you can get a solution of x cubed equals px plus q out of that same formula. So that's what this part is about, just by substituting negative p, replacing p by negative p. Okay, so here is the formula that we're going to use, this new one, which is a solution to the equation x cubed equals px plus q. Now, this is the interesting part. In this book, Algebra was what it was called, and it was published in 1572, Bombelli presents this cubic, x cubed equals 15x plus 4. Okay. It's not hard to check that 4 is a solution. So because 4 cubed is 64, and that's equal to 15 times 4, which is 60 plus 4. So 4 is obviously a solution to this. But when you substitute into the equation, into the cubic formula, you get the square roots of negative numbers here. You get the square root of negative 121. And this shows the detail of that. Okay? So, he tried various substitutions to make this make sense, but they didn't help. All right? So, with obvious frustration, Cardan was the original person who did this. He called such cubics irreducible and he gave up. Okay? But Bombelli found a way to make progress that was similar to Pharaoh's, and that is he guessed correctly at the solution. He reasoned that if x were to be real, then these two cube roots must be what we today call complex conjugates. Numbers of the form a plus b times the square root of negative 1. They weren't using I at this point. And a minus b times the square root of negative 1. He just came up with this. He realized that that's what it would have to be. And then setting the first one equal to a plus b, the square root of negative 1, and the second one the other way, then he solved those equations and found those cube roots. And the cube roots turn out to be 2 plus the square root of negative 1 and 2 minus the square root of negative 1. And when you add those together, you really do get 4. So, by not being afraid to deal with square roots of negative numbers, Bombelli had succeeded in vindicating the formula. This is real history. This is what happened. Okay? So this was the first time that people thought, okay, gee, maybe these square roots of negative numbers are useful for something. But there was a lot of controversy, and many mathematicians did not accept the square roots of negative numbers at this point. It took several hundred more years before that happened. And then this part here is the last part, and it's important to read this. Not all rules are still good. When we use the square roots of negative numbers, we have some problems. Because the square root of negative 1, on the one hand, would be, negative 1 would equal the square root of negative 1 times itself. And if you can multiply under the square root sign, then that would be the square root of negative 1 times negative 1, which is 1. And that would say negative 1 equals 1. Well, we can't have that. So we're confronted with another Hobson's choice. We talked about this with probability, where geometric probability, where the probability of picking one particular number has to be 0. And this is a similar one. So we had to do something. You either have to give up the square root of minus 1, or we have to give up the rule that the square root of a product is equal to the product of the square roots, in the case where a and b are negative. And mathematicians chose that course because the square root of minus 1 has proved to be so useful, and that's one reason why historically they started using I instead of the square root of minus 1 to avoid that confusion. All right. So that's the part of this document that I would like you to read and understand the algebra that's involved. And if you have questions, record them. Okay, that's it for this.